This month, we have a space spectacular. After over a decade of chasing a comet through the solar system, the space probe Rosetta finally reaches its target. And we'll be reporting from the European Space Agency's Mission Control in Germany. Rosetta is one of the most exciting and ambitious missions ever attempted, like something straight out of science fiction. There's a 6 billion kilometre journey, a rendezvous with a comet, and then, if all goes well, a landing on the surface using harpoons and grappling hooks. It's a wonderful scientific mission, but it's also a remarkable feat of engineering, and I'm going to meet the people who are in control and find out how they're going to pull this off.
And here in the UK, we'll be discovering why comets are so important to study and viewing one visible in our skies right now. Welcome to the Sky at Night.
Welcome to the European Space Operations Centre Mission Control in Darmstadt, Germany. This is where Rosetta's most critical manoeuvres are planned and then carried out. We'll be getting a tour of the spacecraft itself and a look at the latest images from Rosetta, which have given scientists 1 or 2 surprises.
And I'm here at the Open University in Buckinghamshire, where one of the key instruments on the Rosetta lander was designed and built. We'll be finding out more about comets and how they're helping us unravel mysteries of Earth's past and maybe looking into the origins of life itself.
And there's a comet visible right now in the night sky. Pete Lawrence will be showing you how to find it and how to take a great comet photo.
Comets are probably one of the most spectacular and enigmatic objects we see in our night skies. For millennia, they've caused us to wonder, what are they and where do they come from? Even 1,000 years ago, we recognised their distinctive shape. In the 11th century Bayer tapestry, Halley's Comet is carefully stitched, showing 3 main parts to a comet. A solid nucleus surrounded by a halo called a coma, and then a long, streaming tail. With the advent of photography, comets have provided breathtaking images and revealed features that cannot be seen with the naked eye. Multiple tails are often revealed on photos. A very straight gas tail is caused by the solar wind ionising gases as they're given off, making them glow. It always points directly away from the sun. The more familiar, diffused, often curved tail is made up of dust which streams behind the comet, but which is also slightly deflected by the solar wind. Recently, we've been able to get an even closer look at a comet. In 1986, space probe Giotto took these remarkable images as it flew past Halley's Comet. In the past 30 years, there have been a number of missions that have flown past comets. And what they've discovered is a central nucleus 1 to 10 kilometres wide. Comets also are surprisingly black due to the high carbon content. The carbon is mixed in with ice and rock, and as the comet approaches the sun, that ice vaporises, producing a coma and then the glorious comet's tail. The tail can be very long indeed. Comet Hyakutake was about 360 million miles long when it appeared in 1996. When the Earth passes through the remains of a comet's tail, the result is an often spectacular meteor shower, as dust particles burn up in the Earth's upper atmosphere. It's only when comets approach the sun closely enough to become active and brightly lit that they become visible to us. To date, we've detected over 4,000 comets, but we know that there are billions more out there. We think they're the leftover detritus of the formation of the solar system some 4.5 billion years ago. And as such, we can use them as tiny time capsules, giving us a window into our distant past. Now we hope to get an unprecedented view of a comet. The snappily named 67P Churyumov-Gerasimenko was discovered in 1969 and is what is known as one of the Jupiter family comets, as they've been swung into their orbits by Jupiter's gravity. Picked from obscurity, it has become a scientific celebrity as the target for the Rosetta mission. And with Rosetta approaching it, we're beginning to get images of the comet for the first time, and it's throwing up some big surprises. Chris is in Germany looking at the latest images hot off the press.
Letting me loose in ESA's mission control is a bit like letting a child loose in a sweet shop. Here, look what I found. This is a model of Rosetta and it's completely accurate. The real thing weighed 2.9 tons on launch. This one's not quite that big, but you can see these long solar panels, which in real life are 32 meters long, and they need to be that size to capture the faint light of the sun, and so that Rosetta can be powered all the way out in the outer solar system. It's got this beautiful communications antenna here. This can point towards Earth, so it can send its signals back to us, and then on the back, all of the instruments. This is the side that will face the comet. You can see here in particular the two cameras of the OSIRIS imaging system. Those will provide the scientific images and they'll help us select a landing site for Philae. This is the little lander that will somehow touch down on the comet. On August the 6th, Rosetta went into orbit around the comet, and so now those cameras are providing vital images to help the team choose their landing spot. But as Dr. Holger Sierk shows me, those images have provided quite a surprise already.
The early images taken beginning of July, when it just barely started to resolve, were a surprise. And it looks like two bodies sticking together. So that was quite obvious right from the beginning, the first days, early July.
The most recent ones I've seen make it look a bit like a rubber duck or something like that, or at least a small head on a body. Is that because it's two bodies that have stuck together, or could this shape have appeared some other way?
I like the rubber duck a lot. So we don't know it yet. I mean, it is a surprise, and we'll have to find out why the body looks like this. So it could be two pieces right from the beginning. It could also be a bigger block that just had some eruption sideways and just carved like the shape we see.
So the duck, if that's what we're calling it, is about 3 kilometers across, something like that?
Yeah.
It must make planning what you're going to do with Rosetta harder, and that planning depends on the images that your cameras are providing.
It makes planning harder, but also more fascinating.
Okay.
And so we are now in the process of laying out the mapping sequences.
Yeah, and the rest of the mission depends on how the quality of those maps as well.
Yeah, and we will also remap because the shape is going to change. We'll watch it on the way in, so to the closest point to the sun. So we'll see the activity rise and the comet be more and more active and then die out again, calm down. We know that the comet is releasing dust, and we want to study these areas there where activity is formed, where dust is moved away. And so why is it happening here in this area and not in others? The physics of comets is not well understood.
So the immediate task for OSIRIS is to produce a three-dimensional map of the surface. Can you show us how far you've got with that?
I can show you with the current state.
Just looking at this shape model here, it's hard to understand where you'd safely put down this lander. I mean, is the obvious thing to go for? There's this big flat face here. That seems safest to me.
Yeah, that's very obvious. The tricky thing is the sun is coming up. So if you project the illumination condition into November, you'll see that it's not so favorable on the large side, on this bottom side.
You don't want to land in the dark.
And you don't want to land in the dark. So landing will be a challenge. I think they will do a good job. I'm convinced about this and find a good spot. Perhaps on the on the back of the duck. We'll see.
Yeah, okay. Well, prediction for the back of the duck. That's excellent. With Rosetta now in orbit, every day we see new critical and stunning surface detail on the comet. And with the lander due to be released in November, we'll be keeping an eye on more pictures as they come in over the next few months, and as the landing site is chosen and confirmed.
Rosetta and the lander module carry more than 20 scientific instruments between them, which will be sending back data. Here in the UK, the Open University is home to the team in charge of a key instrument on the Rosetta lander that will actually analyse the comet's samples. Comets are fascinating because they give us a snapshot into the ancient solar system. And by looking at what they're made of, we can understand how our world was formed and maybe even how life began. Dr. Natalie Starkey is one of the comet research team here and has been studying particles of dust from the Earth's upper atmosphere. Amongst the normal dust and pollution, she finds particles which are from the tails of comets.
So this is one of the most interesting particles I've analysed, actually, because it contains all sorts of material. We've got amorphous material up in the top and also over to the right, and
That looks like gloopy.
Yeah, exactly. It's kind of it's more organic kind of material.
It's organic. That sounds interesting.
Yeah, it's not life. So people will think of organic material as life, but actually
Yes.
what we're talking about is carbon, hydrogen, nitrogen, oxygen bonds, and it's kind of organic precursor material.
Right.
The rest of the particle is quite rocky, what we describe as rocky.
So what sort of analysis do you do?
Well, we try and do everything because this is a sample of space. You know, we don't get many of them.
So how many have you done in your career so far?
I've measured about 50 so far, maybe 5 that are really, really interesting, that can tell us a lot about the kind of time we're looking into, this really early material.
4.5 billion years ago.
Exactly, exactly. So we want to throw every single instrument at them that we have, you know, all these really advanced techniques, because they're precious samples. And as we're analysing it, we're destroying it as we go, but...
Taking bits off the top.
Exactly.
Yes.
But we're getting some numbers at the same time. And the next images you have here show some of the beautiful isotopic images we get.
So when you say isotope, what do you mean?
Well, an isotope is just a special type of an element, really. It just contains a different number of neutrons in it. So we're just looking at these very little variations.
So these isotope distributions, what do they tell us?
Well, what we can see from this particle is that actually there's quite a lot of variation in this single piece of dust. And actually this allows us to trace not only times of when that comet might have formed a little bit, it doesn't give us a date, but we can kind of relative times, but also processes, kind of what happened to those isotope ratios, because they change depending on the temperature and the conditions that comet formed under.
I see. So isotopes actually sort of give you a location and a time scale.
Exactly. So we start to be able to place things relatively to each other. And what we find with particles like this really interesting one is that it contains pieces that are a bit mixed. So it's not just all one composition. It didn't all form in one place. This piece of comet actually contains other pieces of comet that formed in different places all over the solar system.
And somehow have all come together.
Somehow came together at a later date. So our understanding of comet formation is really led by research like this. When we use these particles from the stratosphere, we don't know from which particular comet they've come from. But one time we've actually been into space and we've sampled a comet, and it was the Stardust mission, which landed back on Earth in 2006. It was a NASA mission. And what they did was actually just fly through the tail of the comet. So all the material coming off, they just collected this as impacting particles into the collectors. And this mission was really groundbreaking. So our very simple comet model is that they formed far from the sun, and they only contain material that formed far from the sun in the cold outer reaches of the solar system.
Which would make sense. If they're formed there, that's the material.
Which makes sense.
Yes.
But actually what Stardust showed us is that this comet called Wilt 2 contained material that was formed also in the inner solar system. So it contained material that is very similar to what we see in asteroids. So it's a little bit complicated. We probably have asteroids at one end, comets at the other, but now we think there's a bit of a continuum in between, and so we need to go and measure more comets to really find out what this continuum is and what's going on, really.
Yes. So I guess that's where Rosetta comes in.
Exactly.
So, in your ideal scenario, sort of dream wish now, what would you like to get out of Rosetta?
For me, it's all about the landing, because I want to drill into that comet and get some of the samples and find out what it's made of. It will hopefully tell us how far from the sun potentially this comet formed, and what kind of processes it's undergone in its lifetime. So where all those little pieces that form that comet actually form themselves, whether it was in the inner solar system, which will be a bit of a surprise, or whether it was way away from the sun. So this is one of the things that will help us build up that picture of the comet, and its life history, basically.
Well, very good luck for it all, and I'm really looking forward to seeing some of this data coming out.
Thank you.
Thanks, Natalie.
Every decade or so, we get a spectacular comet passing close by the sun and giving us a display that dominates the night sky. But there are actually comets visible much more frequently than that, and Pete's here to show you how to see one that's in the night sky right now.
Typically, there are lots of faint comets visible in the night sky, but occasionally one will get bright enough so that it can be seen with a small telescope or even a pair of binoculars. Now, there's one of those visible this month. Now, this particular comet is relatively easy to see so long as you know where to look. This newly discovered comet, called C2014 E2 Jacques, can be found by locating the bright star Capella. At this time of year, it's the brightest star in the northeastern part of the sky. At the start of the month, the comet lies in a patch of sky approximately 1 fist width at arm's length to the right of Capella. By the 15th, it'll have moved up the sky to sit left of the star Murphach in Perseus. Look up from Murphach and you'll eventually arrive at the W-shaped constellation of Cassiopeia. During August, the W appears on its side. After the 15th, the comet tracks up towards Segin, the star that marks the left-hand end of the W. It's so close to it on the nights of the 22nd and 23rd of August that a pair of binoculars pointed at the star should include the comet in the same field of view. At the end of August, E2 Jacques moves into the constellation of Cepheus, and although it should be fading, will hopefully remain a binocular target. Now, you should be able to see this comet quite easily with just a pair of binoculars. But if you've got a digital SLR camera, a decent lens and a tripod, you can try taking a photograph of it to get an even better view. Put the ISO or sensitivity of your camera high and use an exposure of 30 or more seconds. Open the lens wide and set your focus to infinity and take a photo of what you think is the right area of sky. Use a remote trigger if you can to avoid camera shake. Now, hopefully, if you're in the right area of sky, you should be able to pick out a little fuzzy blob. Let's have a look. Just like that. And that should be the comet. The comet nucleus itself is, of course, not only tiny, but incredibly black. So all we're looking at is the sun's light reflecting off the dust it's emitting and from glowing gases. The fuzzy, diffuse nature of a comet does make it quite difficult to find, first of all, because it looks much fainter than a star. But once you've identified it in your photograph, the thing to do then is to centre up the frame so you're pointing directly at the comet, and then use a lens with a longer focal length to get closer in. I'm going to use a telescope for this one. Now, as most comets move relative to the stars, if you take a long exposure shot on a tracking mount which keeps up with the stars, the comet will appear blurred. One way around this is to take shorter exposures and, using image processing software, combine the images using the comet's head as the reference. This will make the stars appear like dotted lines, but the comet will really shine through and hopefully show its true colour, an astonishing green glow. And that's a very characteristic colour seen in a lot of comets. And that's due to the gases which surround the central core of the comet, the nucleus, and they're giving off this amazing green coloured light. It's the sun's ultraviolet light that causes the gases, mainly cyanogen and diatomic carbon, to fluoresce. And it's one of the features of comets only really picked up by photography. Comets make fantastic photographic subjects, and if you do manage to get a long exposure shot of it, that'll pick out some good detail and give you a great image to show off as well. If you do get a nice photo, share it via our website at bbc.co.uk/sky at night, where you'll also find my guide on how to find E2 Jacques.
8, 7, 6.
It's been more than 10 years since Rosetta was blasted into space at the start of an epic mission.
Décollage.
It's taken more than £1 billion of investment and decades of scientific work. So why does visiting a comet warrant so much investment? And how on earth are we going to achieve the mission's objectives? Chris has been finding out.
One of the questions this mission sets out to answer is a surprising one. Could this water, this precious liquid that makes all life on Earth possible, have been carried here from space on icy asteroids and comets which have bombarded the Earth over the millennia? We think of ourselves as the blue planet with vast amounts of liquid water. But if all of our water were gathered into one place, well, this image shows how little there really is on Earth. Nevertheless, it would take perhaps 100 million comets to bring us all this. It seems ridiculous that all of Earth's water could have been delivered from space, and yet in the early days, Earth would have been a hot world. Any water would have boiled off almost immediately. And so water must have arrived on Earth and the other rocky planets later. And one of the leading theories is that it was delivered during a period of heavy bombardment nearly 4 billion years ago as icy comets and asteroids slammed into the Earth. We think there might have been enough comets hitting the Earth to supply all of our water, but one of Rosetta's tasks is to look for hard evidence that they really did. Water can contain different kinds of hydrogen, different isotopes. And the ratio of these isotopes gives Earth's water a distinct signature. Rosetta will analyse the water on the comet to see whether it shares that same distinctive signature, real evidence that our water could have come from comets. But that's not all. Rosetta will also be looking for complex chemicals like amino acids, which form the basis of life, to find out whether these too could have come from comets. These are some of the most profound questions in science today, and that's why this particular mission is so exciting and so ambitious. To answer these big questions, Rosetta has to do something really new, land on the surface and drill down to analyse what lies beneath. But before you can do that, you have to catch the comet. It's an incredible undertaking, challenging in just about every respect, and it's made Rosetta a huge engineering project. Now, the most crucial moments are finally upon the team. Andrea Akamatsu's been working on Rosetta since the earliest design stages, and is the flight director.
It's one of the most challenging space missions ever. Nobody has ever gone to such an irregular body, such an active body, with the need of such a high accuracy of flying the spacecraft around the body. So it's definitely something new, it's unique in the history of spaceflight, and it's fantastic.
How do you go about rendezvousing with the comet?
What we wanted to do, we wanted to reach the comet and stop there and start orbiting the comet. So we had to slow down the spacecraft compared to the comet and slowly approach it. And once we were close to it, then we could start our mission. At the end of a 10 years journey, we now start exploring a new world, and we have to characterize it completely. We don't know anything of this new world. We have to characterize the gravity field first. We have to characterize how it's rotating. We know the shape. We have taken a couple of images, but we have to characterize it to a level such that we can then orbit and land.
And of course, this is a changing body as well. We expect the comet to become more active as it gets near the sun. We've already seen some activity from the comet. How do you have to take that into account? It sounds like a scary place for a spacecraft to be.
Indeed. Also, it's a scary place to be with a spacecraft which has huge solar rays. Fundamentally, the comet is releasing material and gases. So we are going to a windy place with huge sails. And it's not easy to navigate around a body like this. But this is the mission we have, and we will do it.
A lot of science will come from the main spacecraft, but the lander is very, very exciting. Tell us about that. How is the lander going to touch down on the comet?
Well, the lander is, for sure, is the most fascinating part of this mission. You can imagine we are landing on a body that is far away from the Earth, a body that is so irregular. So it definitely is the most fascinating. And I would say technically, is also the most challenging for us. We have to release the lander when we are flying in front of the comet, which is a very bad region for the wind. The wind is expected to be very high.
Because that's where the sun's energy comes
in. Right. The sun is heating the surface of the comet and is blowing out a lot of gases. So we have to fly very fast in front of the comet, release the lander. The lander will slowly fall onto the surface of the comet.
Just pulled by the comet's gravity?
Right. It's pulled by the gravity of the comet. There's no active system to slow down on the lander. And then it lands, it anchors itself. It has 2 harpoons underneath, and it will be fired onto the surface, hoping to hook it there.
And so the lander will do its thing, it will send back information, but the mission goes on even after the landing. What happens next?
The mission in itself is spending 18 months at least around the comet. There's much more we have to discover with the science instruments on board Rosetta.
So taking together, it's 18 years of work for you. What does it feel like to be this close to starting to get data back?
Well, when I started working on Rosetta in '96, it looked so far away, the whole thing. But my life has gone through, in my professional life and my private life, have gone through these 18 years, and now we are there, and it can't be anything better than what we are living right now.
Well, I hope it all goes well. We look forward to seeing the results. Thank you very much.
Thanks a lot. Thanks.
The Rosetta probe is an astonishing piece of craftsmanship, and here at the Control Centre, they have what's called an engineering replica of it, kept in pristine, space-like cleanliness and used to test all of the software on board. This engineering replica is obviously missing its solar panel wings, but other than that, it's the perfect way to admire all of Rosetta's features. The whole thing weighed 2.9 tons on launch. But 1.6 tons of that was fuel. "24 tiny thrusters give precision control. And Rosetta itself carries 11 onboard instruments, which all have to share the same power supply. There are 12,000 separate electrical connections. They alone took 3 years to build, and all of them have to work. Over the next 3.5 months, Rosetta will be working its way closer to the comet, taking images and measurements with its instruments all the time, helping us to understand what's going on and trying to select a site for the all-important landing. After nearly 20 years of work, I can't imagine what the team here must be thinking as they get close to these historic moments. We're going to explore a brave new world. We're going to learn so much, not just about this comet, not just about the origins of the solar system, but also about what happened a long time ago here on Earth. It's a really, really exciting time.
Of course, we'll be following Rosetta's progress over the next nail-biting couple of months as it spirals down towards the comet, releasing the lander with its grappling hooks ready for drilling. And next month, we'll be looking at new worlds discovered on planets outside our solar system. In the meanwhile, get outside and get looking for comets. Good night.
Let's hitch a rocket to the moon. Open out the throttle. Steer towards the sun. Rosetta's in her stride. Surf the comet's tail on an astronomic trail.